All right. Hello, everyone. My name is Chris Meert. I'm a graduate student at the University of Michigan. Today, we'll be talking about detection concepts for active interrogation. This is building off of Abbas's presentation yesterday. So I guess be sure to type in chat if you ever see any sound or video problems. Otherwise, we can get started. So just to start with some background motivation. Yesterday, Abbas discussed a lot of the underlying physics for this active interrogation. So mostly some of the important figures to remember is related to the passive emissions of special nuclear material. We're often interested in these time-correlated neutron emissions because those are going to be characteristic of the special nuclear material. Think about fission, which will emit neutrons nearly simultaneously in time. And you can also look at photon signatures similarly. But if you look at passive emission rates, say from plutonium or uranium, you find that there are very different magnitudes. So plutonium-240, which will undergo spontaneous fission, that may be emitting neutrons on the order of 1,000 neutrons per second per gram. So you might have luck detecting that with passive detectors. But in contrast, something like uranium-235, which is the main component of highly enriched uranium, that'll only be emitting 3 × 10⁻⁴ neutrons per second per gram. And so that has potential to challenge your detection systems. How does that physics tie in with our application space? Well, consider just the Port of Los Angeles. That receives about 26,000 cargo containers per day. You can see an example cargo ship on the right. So an essential question may be, should we inspect all of these to ensure safety? If we did want to inspect each of these for 1 minute, that would correspond to roughly 430 inspection hours per day, far more than the 24 hours in the day. And trade is time sensitive. And so the challenge will be, how can we reduce our inspection time required to ensure safety of these cargo containers? So potential to shorten that inspection time to overcome, say, weak source terms would be active interrogation. On the right, there's just an example system called nuclear car wash concept. Something you might do is have a cargo container on a truck, drive over a source of neutrons, and then detect signatures in detector arrays, which you can see in the teal in this slide. And so, of course, there are going to be advantages and challenges for this system or systems that take advantage of active interrogation. The clearest thing will be that the signatures will be stronger than passive because we'll be inducing signatures from reactions that hopefully are much more than the passive signatures. And we can use this radiation source to penetrate the radiation shield, and that could be used, say, in cargo containers. There will be challenges. Since we're using an external source of radiation, we may be increasing dose to personnel. We could contend with activation of cargo if we're going to induce radioactivity. And of course, with pieces of equipment that are perhaps complicated or relatively new, there will be a cost component to be considered. And so just largely when we do active interrogation, there'll be just this general overview of the process. We're going to have to irradiate cargo, either with photons or neutrons. We'll discuss each of those potential sources in the slide set. We're going to induce reactions with these external irradiation sources. If we're using neutrons, we're looking for things like fission of fissile or fissionable material, or we can look for a neutron capture, which will produce gamma rays. If we're using a photon source to inspect cargo, we'll either be seeing gamma N reactions, so photons of sufficient energy can cause the emission of a neutron. We'll look for photofission. There's also potential for nuclear resonance fluorescence, or NRF. And as we induce these reactions, we'll be looking to detect their actual signatures, either photons or neutrons, as far as type goes, but also in time domain. We can look for prompt signatures, or we can look for delayed signatures, which we'll talk about in some later slides. First, we can start with neutron interrogation. We'll start at the beginning with sources. So, of course, we may be more familiar with isotopic sources of neutrons. Examples, they can just be encapsulated in, say, aluminum or steel, like we show on the upper right. You can see just different sizes. And there'll be materials like americium lithium, or AMLI, plutonium beryllium, or PuB, or californium-252. The AMLI and PuB are alpha N sources, and so they will emit specific spectra consistent with that reaction. Californium-252 undergoes spontaneous fission, and so we'll see watt spectrum neutrons emitted there. And then, of course, we can also use neutron generators, which are either DD or DT. And the main consideration is, you want a specific strength to cause a sufficient signature, but consider, say, for our isotopic sources, they're always on, The plutonium is always decaying and irradiating the beryllium with alpha particles. Your isotopic source strength may vary with time. Say Californium-252 has a half-life in the order of 2.5 years. So as soon as you fabricate that source, you'll see its strength will reduce with time. And as you have these sources that are always on, you have to consider the security for those high activity sources. You will not want someone to take it. And so all this steers us towards neutron generators. An example is shown in the bottom right here. You see it's a relatively small form factor. So to get more detail of these neutron generators, largely they are particle accelerators that leverage the advantages of these fusion reactions, either deuterium-deuterium or deuterium-tritium. Those reactions are shown in the center of the slide. You see that we're using these fusion reactions to get either 2.45 MeV neutrons from the DD or 14.1 MeV neutrons from DT reactions. And so they make these generators of these two different models, and you can even change its energy by using, say, moderation. So you can add, say, hydrogenous material to moderate these neutrons to thermal energy, but that will affect your intensity. There's several companies that make such generators, and you can find information on their websites. Companies like Adelphi Technology or Starfire or Thermo Fisher, which is the model shown. And so these are largely mature technology. There's several available, and the relatively small form factor is a plus for these. With these generators, now we're going to look at what signatures we want from the neutron generator induced reactions. Again, we'll be looking for, say, multiplicity of fission neutrons. This is of a lot of interest to us because we're relying on these time correlated emissions of neutrons to identify its SNM. This is a plot on the right from some literature that shows the different neutron energy spectra from either prompt or delayed signatures. You can see that, say, prompt has a harder spectrum. So if you want to look for higher energy neutrons, prompt will give you much better luck. If you look for delayed signatures, you can look, say, in different time scales, but you're restricted by their energy, highest energy. If we look for gamma rays from these neutron reactions, may largely look for capture gamma rays. So that's the neutron absorbed by an isotope and emits a gamma. That energy is going to be characteristic of the isotope that absorbed the neutron. So we might see some spectrum later on in this presentation. And we can also look for delayed photons from fission. So say if we're using a pulsed neutron source, we can look for these photons in between the pulses in that microstructure. Once those signatures are emitted, we of course need a reliable system to detect them. And so when we're looking to detect photons, we'll be looking a lot at, say, scintillators or semiconductors. Scintillators generally are economical. They're, of course, typical like sodium iodide or BGO. And there's even more work for lanthanum bromide, serum bromide, relatively new materials that can have better energy resolution than sodium iodide. So you can see, say, example of lanthanum bromide detectors, various sizes. You can see that the crystals are integrated fully with the photomultiplier tubes. You can attach your own voltage dividers. If we look for, I could also add in HPGE. So semiconductors are also quite useful for photon detection because HPGE has a very good energy resolution. They just typically have to be cooled. So on the bottom right, you can see various HPGE detectors. Most of them are attached to dewars that are filled with liquid nitrogen, and that's designed to keep the temperature sufficiently low. If we're looking for neutrons, in contrast, we could either rely on capture-based detectors, things like helium-3, or perhaps boron-based detectors. But a lot of new work is focused on scatter-based neutron detectors, say plastics or organic scintillators. So an example is stilbene on the upper right here. Stilbene crystal under some UV light causes it to emit its own scintillation light, that purple. The most important thing as we look for these detectors and try to decide what detector to use, well, we want high efficiency so we can detect the signatures. And you can get by making a decision based on the time domain that you're interested in. If you're looking for delayed signatures, helium-3 may suffice, and there's been a lot of work with helium-3. But if you want prominent signatures that are emitted much shorter time scale, you might find yourself steered more towards the scatter-based scintillators. So we can talk about a couple examples with this neutron interrogation. This first one is differential die-away analysis, or DDAA. Conceptually, we're using neutrons to interrogate and then we're looking to detect neutrons after a neutron pulse. And so the specific work from this literature uses a DD neutron generator and irradiates several targets: uranium, plutonium, and tungsten. And we can talk through each of these plots and discuss the data series as well. And so probably the easiest one to interpret is the lower right, where they irradiated tungsten with the neutron generator. First, the black dotted line is BKD, or background. That's when there is the tungsten is in the measurement setup, but there is no neutron generator on. You see the dotted black line. So we're just seeing a steady state background. Then for the red data series, that's if there were no tungsten, but we turned on the neutron generator. And that's in line roughly with the blue case. That's neutron generator irradiating the tungsten. And so one, we see the pulse nature of the source, where the neutron generator is turned on and it has some tail of its pulse, and then it will return to the background level. This is partially expected because tungsten is not fissile or fissionable. So the tungsten is just presenting perhaps a scatter source for neutrons. You can see perhaps in the blue versus red, you can see a slightly different tail. That is the added characteristic of the tungsten. If we move to something like fissionable material, like depleted uranium, we would move to the left plot here. We're again recording counts on the Y as a function of time. Background stays the same, dotted black. Here you can see in the blue data series, it stays higher for a longer period of time. That's because the fission chains are persisting after the neutron generator has finished firing. And so you could use this to identify, based on how long it takes for this pulse to return to background, if you have fissionable material. Again, you see this gap from blue to red. A slightly more interesting case is with plutonium. So again, this reactor grade plutonium. Here, the background, you see it's around 10 to the 3, dotted black line, much higher than these other cases. And that's because we're the dotted black, that's with the source, without the neutron generator. So we're seeing the passive emissions of neutrons from the plutonium. When we turn on the neutron generator, of course, we still see a nice increase in neutrons. We see a difference in the tail. And you could even tell from this plot, you would know that plutonium was here based on just the neutron detection rate without the generator. And then lastly, the enriched uranium case. Here, there's a lot of fissile material, the uranium-235. And again, you can see a much longer tail, so even different from, say, the depleted uranium case. The neutrons that are emitted from fissions are able to interact with the room, thermalize, and cause even longer fission chains in the uranium. And so this blue tail persists for much longer. And so you could use this looking at the shape of the counting curve, look at the amplitude of the curve, and comparing all these to their background cases could be used to detect fissionable or fissile material using neutron interrogation. So that corresponds to neutron interrogation, neutron detection. To give another example is prompt gamma activation analysis, or PGAA. Instead of, we'll still use a neutron generator, but we're also going to look for photon signatures. And so this concept shows a potential system on the right. Here we'd have a conveyor belt that brings baggage into the shielded area that has a DD neutron generator or even a isotopic source, but here this data shows DD neutrons. They irradiate the package, and then we're detecting the photon signatures using our HPG. And so a lot of times they will irradiate, say, hydrogen-rich or neutron-rich material. We'll be looking for their capture signatures. And so the two example plots shown on the bottom tie into that. On the left here is an example HPG spectrum recorded under two cases. One, the solid black line is the system background. And so if there is no source, you don't see any signature in this region. Then they put a Teflon blank, which is the dotted black series. And you see a peak at roughly 2.2 MeV that corresponds to hydrogen capturing a neutron and emitting a 2.2 MeV gamma ray. And so that's an example one signature you'd look for. Something you do more applied is to trend counts in that region versus mass fraction. And so you can use various samples of different mass percentages. So here they chose different nitrogen mass fractions. Nitrogen would be of interest because nitrogen material may be consistent with explosive material. And you can trend the count rates on the Y versus that mass fraction. You see, well, of course, as you increase the mass fraction, you increase the count rates for these various nitrogen signatures. So black circles for a 5.3 MeV, and also these triangles for a 1.8 MeV. And so you could use these, you could use standards to establish a count rate, and then interpret your own gamma spectra to tell you whether you detect contraband. After we discuss those two examples with neutron interrogation, we can also discuss photon interrogation. Again, we'll start with the actual sources we'll be using. You can use isotopic sources of gamma rays just in general research. We often use, say, cesium or cobalt to calibrate detectors, but they're generally not used for photon active interrogation. You may be limited by the energy and the half-life, and that makes it very difficult for you to use isotopic sources to induce, say, photonuclear reactions. And of course, the same source security potential applies. And so something far more prevalent for photon interrogation is going to be X-ray generators. So we'll be producing X-rays, traditionally bremsstrahlung sources. Like I've shown on this slide, there are two examples. IBA Rototron, you can see just sense for size, there's a step ladder back there. Or Varex linear accelerator, Linotron, like I've shown in this picture, and sense for scale, this is probably roughly meter long. There is additional work, say, to look at tunable monoenergetic photon sources, but those largely existed in the research space as people try to learn more about those sources and make them more economical. Just some more detail on the linear accelerator side. Largely, these sources work where you accelerate electrons, which are produced from, say, a cathode source. You have to accelerate them using some electromagnetics, and you want to accelerate them to high kinetic energy. Shown in this figure from Wikipedia. Those electrons then hit a high electron density target and undergo radiative losses, producing bremsstrahlung radiation. Those bremsstrahlung spectra they have broad energy spectra, and they'll have a long tail. And so an example spectrum from the null radiation detection book shown on the right. Here they used 5.3 MeV electrons on a gold tungsten target, and this is a log scale in the Y. You see it's a smooth spectrum here, and it reaches its maximum at 5.3 MeV because bremsstrahlung will result in it would prefer for these low energy emissions. And so you don't get a monoenergetic spectrum with bremsstrahlung sources, you get this broad energy range. In any case, these are often pulse sources, so we can look more at prompt versus delayed signatures. And again, just drive home the point, they are not monoenergetic like you would get with DT and DD neutron sources. So first example with the photon interrogation is nuclear resonance fluorescence. We're going to look for photon signatures. In this sort of technique, we use the high energy photons to excite the electromagnetic resonances within nuclei. And those are going to be unique and discrete energies for each isotope. You can see example on the upper right, you have some X-ray source, you have to collimate it, and you want some amount of the photons to reach whatever object you're inspecting. And this object is one that has the characteristic resonances that you're searching for. So you'll excite them to the resonance, emit, and then they'll relax, go back to ground state, and emit the photons that you want to detect in your detector. This generally has some advantages, say potential to detect the small quantities of material in the shielded scenarios, but there is going to be some disadvantage with photon background. Just to give an example of a result is on the lower right. So here there's a couple cases plotted. First, in the black here, you can see the irradiated manganese that produces two spectra or two peaks here, and where I'm outlining. Then they added some HEU, and that gives rise to the red data series. You see more peaks, which they've marked with the green arrows. You can see the increase over background, and you can see all these other, like each of these peaks will correspond to a characteristic excitation level. And so not only can you identify material, you can identify the isotopes that are within that material. An example of neutron detection when using photon interrogation, that'd be prompt photofission neutron detection. Like the previous case, we're still using, say, a LINAC branch filling spectrum. Here we can irradiate depleted uranium, and we'll be interpreting PSD plots. And so in each of these plots, there are tail to total ratio, so pulse shape ratio. Just broadly, this red discrimination line discriminates photons versus neutrons. So traditionally, based on PSD, you would expect photons to appear below this red line, neutrons above the red line, but also pulse pileup, which I believe a boss discussed yesterday, will impact the fidelity of your neutron measurements. So on the upper right is, say, raw stillbeam. So this is detected with a 2-inch stillbeam detector during the DU interrogation without any pulse rejection on. And so you can see a strong photon signature, largely caused by the LINAC. But if you look for a neutron band of similar proportion, you can't find it. It's probably hidden within all these pileups. So that presents one of the main challenges when looking for these prompt photofission neutron detection events. So we often need to find a way to improve our neutron detection. And in this case, this is some work we did, a boss and I, at the University of Michigan, worked with an artificial neural network that could decompose pileup events and recover pulse classification data. And so the two plots here are the result of the ANN analysis. Here on the right, we fed this data set and pulled only pulses that the ANN attributed as photons. Of course, we see these strong photon peak. And at the time, this was some work from a couple of years ago, there were some misclassified pulses, but nonetheless, it could accurately identify the photons. And it also detected some neutrons. So you see the semblance of a neutron band here, which is a great sign, and that we would not otherwise see by just using traditional charge integration. And so there's a lot of work in this area. Of course, people are interested in machine learning. So to summarize some of these techniques, again, we're looking at active interrogation in general. All these techniques will take place in these 3 steps. The irradiating cargo with either photons or neutrons will induce reactions, either neutron-induced reactions like fission or capture reactions, or photon-induced reactions like photodisintegration, photofission, or nuclear resonance fluorescence. And then we're going to detect the signatures from those reactions, or either look for photons or neutrons, and then we'll look for them in different time domains, either prompt emissions, which are very short timescales, or delayed, which correspond to delayed fission events. In general, these active interrogation techniques have potential to improve our capability to detect fissile material. Think about using these intense sources to raise the neutron emission rate of material, in contrast to, say, those passive signatures we discussed at the start of the presentation. And of course, there are always challenges with new techniques, and challenges will persist, and that's part of our research to minimize, say, cost, dose, and also improve fidelity. So thanks. Let me know if you have any questions. If we have additional time, I do have some additional slides we can go through. Thanks. See a question from the chat. It says, overall, how much time does it take for one interrogation from start to finish? So, I mean, that's going to be strongly dependent on whatever system you're using. I suppose this slide probably suffices. Yeah, it will just depend on how strong your radiating source is, on how much material and also how efficient your detector system is. There's typical guidance. You want to have a very quick interrogation so you do not hold up, say, commerce, but I can't speak to any specific quantities otherwise. Let's see. What are the major concerns today with SNM and cargo transport or other applications where active interrogation might be employed? I guess if I interpret your question, I mean, the main thrust of active interrogation is to find smuggled SNM or shielded SNM that's not been declared. So I mean, that's a lot of the motivation. It's just to find, maybe you want to scan material that leaves power plant or fuel cycle facilities, things of that nature. And so that, yeah, that's the concern, just to maintain control and accounting of fissionable and fissile material. As far as other applications, I mean, you could be, there's people who have used neutron interrogation to quantify like soil, components in soil. You can do, you can attribute, say, clay pottery from certain points, certain parts of the country or world based on their soil characteristics. I guess I'd say other, I guess just in general too, to both of those would be cost, time. Yeah, dose, time, and cost. Yeah, so I mean, if you had a source sufficiently strong, you may have to move people away from your inspection area so they don't take extra dose. That could be a concern. Time will, as I mentioned earlier, will always be some part of it. You don't want to pull someone's trailer aside to inspect for days. You need to have a reasonable time component there. Let's see. I think I see just a follow-up question there. Could active interrogation be used for a speedy quantitative isotopic analysis in a lab setting? Yes, I guess I would aim you to or PGAA, prompt gamma activation analysis. You can find a lot of literature where people can find hydrogen, nitrogen, aluminum, magnesium, all sorts of concentrations using neutron interrogation. Another question, why are scintillation detectors used more than other types of detectors in interrogation? Cost, efficiency, or other reason? Yeah, so I mean, there are many factors here. Scintillation detectors have potential to be very fast, and so you can avoid pileup. Scintillators are typically cheaper than semiconductors. So, you know, comparing sodium iodide to HPG on the basis of cost, you know there's quite a big difference there. And that correlates with efficiency. You know, getting a large sodium iodide is much cheaper than getting a large HPG. There's also can be other concerns about neutron damage to, say, semiconductors. I suppose you're not as worried with scintillators. I see a latest question. Will shape of graph mentioned in the slide be the same for all percentage of enrichment? So I suppose that's the differential die-away slide. Let's jump back there. So you can basically see that relationship between this enriched uranium plot versus this depleted uranium plot. Depleted uranium is almost all uranium-238. That's non-fissile. The enriched uranium, I can't remember the precise enrichment of this in this work, but it has much higher proportion of U-235. And so, yes, I believe the persistence of the tail will be related to the percentage enrichment, because the tail is coming from long-lived fission chains that will result from, say, thermal neutron-induced fission. So the question, are there open source data sets on the active interrogation data, say detection time and energy, that we can access like CERN database? I'm not sure for that one. I'd have to direct you to talking to cognizant CERN folks for that. Let's see, what does NG represent from the graph? Okay, let me go up. I suppose, is that also this differential die-away plot? Yeah, so Yeah, so I guess just to drive the point home on this, each of these plots have the three data sets here that I've color coded as well. And NG is neutron generator. Yeah. So detector, the red data series should be largely similar because we're just seeing the neutron generator contribution, something like active background that a boss referred to yesterday. Blue signal is when you're irradiating your uranium or tungsten or plutonium with the neutron generator. Is active interrogation limited to cargo, or can it be used in airports for interrogation? Yeah, so I mean, people are interested in applying this in a wide variety of locations. There is a NIST standard that I believe discusses different size packages that run from, say, rail to small hand carried cargo. So I think there would be motivation there. How dangerous is the level of ionizing radiation produced here to personnel? Yeah, so the machine I've worked with is based on medical technology, and so you can produce dose that it can be dangerous. Of course, you are, when you are using a system that's so large and stationary, you would have to implement, say, collimation and shielding to protect personnel. I suppose even on this, one of these slides, yeah, here with this neutron generator, there is, say, a lead curtain, and there's a beam stop, and I suppose the rest of the structure is also shielded. I mean, it's just a thing of, yeah, shielding the beam in whatever direction it's traveling. So in this case, the beam goes from bottom straight up through the page. But also, you would just like to keep dose low as reasonably achievable, both to the public and to the operator who may be here most of the day. And I suppose if you wanted more quantities, you have to look more at the source itself. So looking more at the manufacturers. Let's see. How often are these used in safeguard applications, like with inspectors in the IAEA? I think most of these are still in the planning stages. If you're interested in literature, you perhaps look at the active well coincidence counter. That does use isotopic neutron source and helium-3 tubes to interrogate material. So that's AWCC. Can't speak much to the accelerator-based methods. Let's see, another question. Does source refer to the material of interest being interrogated? Is that back on this plot? Yeah, let's see. Yeah, so in this list, when I say source, it refers specifically to the uranium or plutonium or tungsten. How does active interrogation compare in effectiveness to other competing methods such as passive muon tomography? That's a good question. I'm not as experienced with muon tomography. If memory serves, that muon tomography can be very time consuming. So in my experience, I think maybe the photon or neutron interrogation is to be much quicker than muon tomography, but I can't speak much to quantity. What differentiates this with passive interrogation? Yeah, so I mean, the main point is that we're using the external sources of radiation. So if we're looking for, to say passive interrogation, more just be passive detection. We'll be relying on, say, spontaneous fission to give us a neutron signature, or say uranium-235 that decays and emits the 186 keV photon. But again, those signatures can be quite weak, and that means longer inspection times, or you need a highly efficient detector system. And so the differentiation here is that we're using external sources of radiation to induce a different set of reactions, which are still characteristic of the materials of interest. Which parameter determines the use of active over passive interrogation? I think the main quantity you would search for is passive source strength of the isotope of interest. So like we showed on, go back here. So again, if we're looking for these passive emission rates, they vary quite a bit by material. Plutonium 240 emit thousands of neutrons per second per gram. You may not have an issue finding that with a helium-3 panel. Uranium 235 does not emit many neutrons, 3 times 10⁴ neutrons per second per gram. It will emit gamma rays as well, but there's associated challenges with those detection capabilities. And so this is, I think, what largely determines why you would want active interrogation. All right, looks like questions might have slowed down. So yeah, I guess in general, thanks for listening to the presentation. Thanks for all your questions and interest. I think we have email addresses if you do come with a question after the fact and let us know. But otherwise, yeah, thanks for listening.